Swayam Prabha. Digital India. Educated India.
So far we have tried to optimize the deposition of the bead when they are deposited next to each other in the XY plane. We have seen that if a bead is deposited in the XY plane, then the next bead has to be deposited adjacent to it at a distance of P equals to 2 by 3 into W, where W is the width of the bead, in order to get the optimal flat surface in the XY plane. Now what will happen if we deposit the bead one over another? So now this will be the case of multi-bead deposition in the vertical direction. Some of the objects made by this method are shown here in this slide. And for more details about this method, one can refer to this particular reference. So theoretically, what happened when a droplet is fall onto a substrate which is flat in nature, the bead looks something like this. However, when we keep on depositing the beads on the top, the base surface is no longer flat. Like for the first bead, it is a flat base, but for the subsequent beads, the base will not be flat. It will be a curved surface. And therefore, the height and width of the bead deposited on the curved base has to be calculated so that the R gap can be maintained throughout the process. If another layer will come on top of it, for example something like this, then in that case this height, what we are talking about, may not be same as the H1. As a result, the R gap will increase or decrease, which is not desirable. But if we exactly know how much the height is going to increase, then we can appropriately maintain the R gap in the process. So let us assume that the cross section of the bead deposited on the flat surface is given by A1 and it is represented by a circle. So earlier we assumed that it is a parabola, but now just for simplification of the calculation, we are assuming it as a circle. So if the bead is circle, now we can assume that based on the height required, the circle will be either inside the base or it will be outside the base. That is how we can represent the deposited bead. Some of the parameters now can be obtained by where W is the distance of this chord which is intersecting by the base, and theta 1 is the angle subtended by the deposited beads at this chord, where this point and the center, this angle is theta 1. Of course, the radius of this circle is given by R, which is nothing but the distance between the center and any point on the periphery of the circle. So considering these geometric parameters, now let us try to find out what will be the height of the bead when we deposit on top of this curved surface. So before that, let us try to find out some of the geometric parameters in terms of the known parameters, such as what you are seeing here is the deposition of the first bead on the flat surface, while what you are seeing here is the deposition of multiple bead now one over another, and the deposition of the beads after then the first layer or the first bead are going to be on top of a curved surface, not on the flat surface. So you can see that the bead base is now the curved surface. So this diagram shows the proper overlap of the two beads. This is the n plus 1th bead and this is the nth bead. So now let us come back and try to find out first of all the area of the bead deposited on the flat surface. So here we can see that W1, which is the width of the bead, can be given as R, which is the radius of this circle, which I have already mentioned that the curve can be represented by a circle. So its two component, the R cos theta 1 will be nothing but this distance from here to here. This will be R cos theta 1, while the distance from here to here will be nothing but R sin theta 1. So if this distance is R sin theta 1, then of course the distance from here to here, that is W1, will be equals to 2R sin theta 1. In a similar fashion, this distance D, which is the perpendicular distance from the chord and the center, can be given as R cos theta 1, which is nothing but the distance from this point to this point, and it is nothing but the projection of this length R on the vertical plane. So it is R cos theta 1. Therefore, the height h1 can be easily calculated now. H1 will be nothing but the distance from here to here minus this distance D, and we know that this distance is going to be nothing but R. If this is capital R, then the height h1 will be equals to R1 minus cos theta 1, because it will be nothing but R minus R cos theta 1, hence h1 will be equals to R1 minus cos theta 1. Now, once we know this, our aim will be now to find out the value of this A1, this area. This area A1 can be first calculated in a simplified manner. So, in order to calculate this area A1, I am going to divide this entire area into two simplified areas, and by appropriately subtracting them, I can obtain it. So, for example, if you look at this diagram, the aim is to find out this area, right? So, I am dividing into two regions, that is area A1, the area is small a1, that is shown here in the yellow color, and the small area, that is A2, that is shown here in blue color. If I subtract the 2A2, the area this shown here of the blue triangle, and assume that there will be another triangle here as well, from this area A1, then I can obtain the area capital A1. So, in other words, I can say A1 will be equals to A1 minus 2A2. So, it is very easy to calculate the area A1, because if I know this is the center and the angle from this line to the vertical line is theta 1, then easily I can say that the area 1 A1 will be equals to R square theta 1. And of course, if this theta value theta 1 is pi, nothing but it will be a complete circle, and area 1 will be equals to pi R square. So, it is just for the verification. Now, let us look into this triangle also. In this triangle which you are seeing here, this length will be R, and the projection of this length in the vertical line will be R cos theta 1, that will be this length, and this distance, that is nothing but the projection of this line on the horizontal plane or horizontal line, will be equals to R sin theta 1. Now, we know that it is a right angle triangle. So, its area will be equals to half of its side. For example, this I am calling it as side P, and this I am calling as side Q. So, it will be half of P into Q. If I put this value of the length, I can obtain the area as A2 equals to 1 by 2 sin theta 1 cos theta 1. Now, I have small a1 and small a2. I can now easily calculate the value of the capital A1, and this area will be equals to A1 minus 2A2. Further, keeping these values of A1 and A2 in this equation, I can obtain the expression for the area of the bead deposited on the flat surface, that is A1, and A1 will be equals to r square theta 1 minus sin theta 1 cos theta 1. It can be noted that we have assumed that the bead shape is going to be represented by a circle, and also this is deposited on a flat surface. The first bead is deposited on a flat surface. Now, as we already have calculated the value of A1, you can see that to obtain the value of A1, we should know the value of theta 1. Now, let us try to find out the expression of theta 1. But please remember that the only measurable parameters of the bead will be the height and the width. Therefore, we will try to find out the value of theta 1 as a function of only the height h1 and the width w1. So, in order to do that, we will just look into these equations once again. So, if I have the equation w1 equals to 2r sin theta 1 and h1 equals to r1 minus cos theta 1, I can easily eliminate r from here just by dividing these two equations. And as a result, I will have 2h1 divided by w1 equals to 1 minus cos theta 1 divided by sin theta 1. Now, if I square both the sides, this will be the expression I will obtain. The square of this term will give me 1 plus cos square theta 1 minus 2 cos theta 1 divided by sin square theta 1. While on the left hand side, it will be 2h1 by w1 square. Now, let us add 1 on both the sides, as you can see here, and as a result, the right side term can be further simplified. Here you can see the term here cos square theta 1 plus sin square theta 1 will become 1, and as a result I am writing 2 directly here. So, it will be 2 minus 2 cos theta 1 divided by sin square theta 1. Let us now take the 2 common from here, from this expression, and let us write sin theta 1 also separately, only one sin theta 1. Another sin theta 1 I am writing with this right side term itself, and it is 1 minus cos theta 1 divided by sin theta 1. Now, you look at this expression carefully. We have already seen this expression somewhere, and it is here, and it is the expression corresponding to 2h1 by w1. So, let me use this expression now, and finally, as a result, I will be having 2 sin theta 1 into 2h1 divided by w1. Now, let us eliminate this w1 from here and to this square term on the left hand side, and as a result, you will have the final equation like this. Further simplifying and obtaining the value of sin theta 1 from this equation, you can obtain sin theta 1 equals to 4h1 w1 divided by 4h1 square plus w1 square. Now, you can see this equation is having only two variables with it, that is h1 and w1, and they both are measurable variable. You can easily measure these two variables after depositing the bead. Now, once we have these two variables, I can obtain the value of theta 1 also easily, and theta 1 will be equals to nothing but sin inverse 4 h1 w1 divided by 4 h1 square plus w1 square. So, now I completely know the area of the bead deposited on a flat surface if I know the value of h1, that is its height, and w1, that is its width. So, knowing it now, our aim will be to obtain the area of the bead deposited on the nth layer. So, if this is the nth layer, what you are seeing here, this is the nth layer. So, this is the bead deposited, but what I am showing here is the curve which is representing this bead. So, assume that this is the circle, here it is in the dash dash because it is inside the previous layer. So, this is the nth bead, and on top of it we are depositing another bead, that is n plus 1th bead. So, our aim is to find out the height of the bead when it is deposited on a curved bead. So, for that, our aim is right now to find out first the area of this deposited bead An. First, our aim will be to find out this deposited area An on the nth layer. So, this area which is shown here in the hatch black color, this is the area we are talking about and calling it as AN. So, this is the bead deposited on nth layer. This area will be equals to the area E K F n plus 1. So, this entire area, right. Then it will be summation of the area shown here, that is nothing but E O N F O n plus 1. And if I subtract from this entire area the area E L F O n. So, let me show it in another color. E L F O n. The remaining area will be nothing but E K F L, or in other words A n. Now, it is very easy to obtain this area. So, let me just clean this region so that we will be able to see all the variables easily. So, first is to obtain the area E K F O n plus 1. So, E K F O n plus 1. So, this area can be easily obtained because we already know this angle, which is theta n, which is subtended by the nth bead at the center, right. We already know this angle theta n. Now, we can find out the angle, this particular angle from the vertical axis to the line joining the center of the above and the point of intersection. Okay, this is the center of the next bead deposited, and this angle will be nothing but pi minus theta n. So, as this angle is pi minus theta n, I can easily find out now the area which is corresponding to this much, right. So, this area, and the area will be equals to r square the angle pi minus theta n. Once I know this area, now I can obtain the area E O n F O n plus 1. So, here first of all I will divide this area into the half, right. So, this much I am interested in first of all, and further I am interested only half of it, right. This angle will be obviously 90 degree, and now I am interested only in this area. And if you remember, we have already calculated once, but again this area will be equals to half of this distance, which is nothing but, if this is r and this angle is theta n, will be nothing but r cos theta n multiplied by this distance from here to here, and that will be r sin theta n. And as a result, this small area which is shown here in the green color will be half of r square sin theta n cos theta n. Now, this entire area E O n F O n will be nothing but 4 times of the same, correct. So, I am writing here 4 times the same thing. Now, obviously, we have to find out the area E L F O n, that is E L F O n. So, to obtain this area, again we can simply find out it. So, again we can simply obtain this area, and it will be nothing but, if this angle is r and this angle is theta n, the area will be r square theta n. As a result, we will be able to obtain the area A n, which is shown here in the black color hatch. Once we got the area of the bead deposited on the nth layer, it is obvious that this area should be same as when the bead was deposited on the flat surface. This is because of the conservation of the mass. You are depositing with the same deposition rate, and even if you deposit on a curved bed or you deposit on a flat bed, the area you are depositing going to remain same. Therefore, let us equate these two areas. That was the area 1 calculated when the bead is deposited on the flat bed, this area 1, and the area we just calculated An. So, after doing it, this will be the equation we obtained. We need to further simplify this equation, and if we simplify this equation, final expression will look something like this. It says sin theta n cos theta n minus theta n will be equals to half of theta 1 minus sin theta 1 cos theta 1 minus pi. So, to obtain the solution of theta 1 from the above equation, you can solve it by using some numerical techniques. Once you apply the numerical technique and you obtain the value of theta n from this equation, it will be very easy for me to obtain the value of the Hn. How? Because Hn is nothing but this height, right? This is the distance between this peak of the newly deposited bead and the peak of the previously deposited bead. So, this difference is nothing but Hn, and the same Hn will be nothing but the distance between these two centers of the deposited bead. On is the center corresponding to the nth bead, and On plus 1 is the center corresponding to the n plus 1th bead. Therefore, the value of Hn will be nothing but this distance, right? And we have already seen the half of this distance. The half of this distance will be what? It will be r cos theta n, and the total will be nothing but 2r cos theta n. So, this is the final expression. Once you know the value of theta n, you can put it into this equation and you can obtain the value of Hn. So, once we know the value of Hn, that is nothing but the deposited height at a curved bead, and we can easily maintain the arc length. Now, let us try to solve a problem to understand this in better way.
So let us now try to solve a problem where it is required to find out the height of the wall after deposition of n layers. So the question is, a thin wall has to be built by MIG-based WAAM process. The single bead experiments first performed on a flat substrate, assuming a circular profile of the bead cross section. Find out the height of the thin wall after deposition of the 10 layers with the same process parameters. So this is the geometry of the bead deposited on the flat substrate is given to us. It is given that the width of the bead is 4 mm, height of the bead is 2 mm, and that is why here it is written h1 equals to 2 and w1 equals to 4. Now we can easily find out the value of theta 1, that is nothing but the angle subtended at the center of the cross section of the bead, that is the arc, by easily this particular formula. It says theta 1 will be equals to sine inverse 4h1 w1 divided by 4h1 square plus w1 square. This we have already proved in our previous slides. So this is the value of the angle theta 1 when the drop is deposited on a flat surface. So the value of theta 1 in this way will be equals to sine inverse. If I put h1 equals to 2 and w1 equals to 4 in this formula, it will be pi by 2. The value of theta 1 will be pi by 2, or in radian it will be 1.571. Now we can easily find out the value of the angle subtended by a deposition on nth layer on the center of the deposited bead. So this already we have derived this equation in the last slide, and now by utilizing this equation we will find out the value of theta n. So we know the value of theta 1 now, so let us substitute the value of theta 1 in this right hand side expression, and as a result the right side expression will be having minus pi by 4. Further simplifying it, the final equation we are having is theta n minus sine theta n cos theta n equals to pi by 4. Now for this case we have to find out what is the value of theta n. Of course, it's a nonlinear equation and hence can be solved by any numerical method. But I will try to solve it by the graphical method. So this is a very good way of solving such simple equations. You can utilize the software called as GeoGebra. It is freeware. You can download and plot the right hand side curve and the left hand side curve and find the intersection point. So like here, this left hand side curve, which is theta n minus sine theta n into cos theta n, is plotted here in this graph. So as you are seeing this green color graph, this is representing this theta n minus sine theta n into cos theta n. Now the right hand side equation, that is nothing but y equals to pi by 4, is plotted here and shown here in the black color. Now the intersection of this green color and black color will be nothing but the solution of this equation. So for that, I just zoomed in this region, and this is the zoom version of the same figure in the localized region here. As a result, I can see the intersection is happening at around 1.15 theta equals to 1.15 radian. So exactly theta n will be equals to 1.16 radian. So I have obtained this value by looking at this graph, which is nothing but the intersection point between the green color graph and the black color graph. Green color graph, which is corresponding to the left hand side equation, and the black color graph is corresponding to the right side equation. Once I have the value of theta n, I can easily obtain the value of the height of the bead obtained after deposition or in the nth layer. So the height of the bead in the nth layer will be equals to On and On plus 1, which we have already seen, and it will be equals to 2r cos theta n. Now the value of r is nothing but equals to 2 here, as you can see, because theta was pi by 2. So we can easily find out the value of r by utilizing the simple geometry, and in this case it is very easy to observe that the value of r will be nothing but same as the height. This is because here my angle is coming to be pi by 2, theta 1 is pi by 2, therefore definitely this r will be equals to h1. So once I know this, I can put 2r cos theta n, and I already know now the value of theta n, that is 1.16 radian, and as a result my value of hn, the height in the nth layer, will be equals to 1.597. Now let us go back to the question. It is asked that find out the height of the thin wall after deposition of the 10 layers with the same process parameter. So of course the first bead or the first layer will be deposited on the flat surface, therefore its height will be 2 mm, that is why 2 is written here, and the next 9 layers will be deposited on top of it. And we have seen that if we are depositing on such curved surface, the height of the bead is going to be 1.597 mm. Therefore the total height after deposition of 10 layer will be 2, which is the height of the first layer, plus 9 into 1.597, and it is coming to be 16.376. So it can be noticed, very interesting thing here, that if you just do not consider the curved shape of the bead and you do not consider it, and you just keep on assuming that the height of the bead is going to be all the time 2 mm, then your nozzle will be at 20 mm above, while the actual height of the wall will be 16.376. So approximately you will be losing around 3.5 mm stand of distance, and that increase in stand of distance will not give you the same mechanical or the metallurgical properties of the deposited bead, which is what giving when it was deposited on the flat surface when the stand of distance was something else. So to maintain the stand of distance between the substrate and the welding gun, of course you have to consider this HN. So from this example we have understood that after 10 layers the height is not going to be really 20 mm, it is going to be 16.37. So after the multi-bead deposition, our focus should be on the multi-layer deposition. However, most of the geometric parameters are dictated by the multi-bead and the single bead deposition only. Once you understood the shape of the single bead and you understood what should be the optimal overlap in the XY plane, or if you are building one bead over another, you understood that what should be the or what will be the height of the bead deposited on the curved beads, then that is the sufficient information to maintain the consistent mechanical and metallurgical properties. However, when you keep on building the part in layer by layer manner, there are few issues arises not because of the geometric constraints or the geometric property of the deposited material, but due to the material properties and the inherent nature of the process. Like for example, when you deposit multiple layers, the first layer undergoes through several thermal cycles, and due to that the mechanical properties and the metallurgical properties are going to change. So this is what we usually discuss when we discuss about the multi-layer deposition. So as you see here in this diagram, it is a component deposited by multi-layer. So several layers are already deposited here. Now on these several layers, the first thing we should measure is the hardness. And this is the build direction. We are moving from bottom to top. In this case, as we are moving from bottom to top, a typical trend is something like this. The hardness usually remain constant in the initial layers, but it usually vary only on the last few layers or the final layers. This is because the bottom portion of this particular part undergoes through several thermal cycles. Due to that, the microstructure here on the bottom portion becomes quite porous. And due to the porous microstructure, the hardness value is usually less. While the newly deposited layers doesn't go through many thermal cycles, and the first layer is definitely not going to go through any other thermal cycle other than the one deposited here. Therefore, the microstructure of the deposited material will be usually fairly fine in that case. Due to the fine microstructure, the hardness also will be high on the top layers and it will be less on the bottom layers. So this trend I'm not saying is very much true for all the materials, but it is quite followed trend, at least particularly in the case of steels. However, different materials may behave differently and this trend may change. But this is the typically trend seen for the hardness variation in the build direction for the part produced by wire arc additive manufacturing.
Another mechanical property usually is the strength of the part. So usually when we build the part by the wire arc additive manufacturing, we prepare the specimens in two directions, that is in X direction and in Y direction in the XY plane, and we also prepare the samples along the Z direction, where the Z direction is the build direction in which you are building. The X direction is nothing but the direction of the torch along which you are depositing. So for example like this. So in this case, this is the direction of the torch, let me call it as X direction, and there will be another direction which will be perpendicular to it, and that will be corresponding to the step over direction, because in this direction you are taking a step over, and that is Y direction. Appropriately, after depositing the block by this technique, we can prepare the samples, and usually for the wire arc additive manufacturing, the ASTM A370 test specimen are sufficient enough. So this is the typical sample for that. Once we prepare this sample, we can perform the tensile test and we can obtain the ultimate strength for the same. So I am here comparing the ultimate strength with the forged part also later on. So it was found that the ultimate strength is about 20% weaker. It was found that in the Z direction, the parts are 20% weaker in yield strength and 11% in the ultimate strength, and it is mostly because of the insufficient penetration with the pre-build or the previous substrate. It was also found that in most of the cases, if the current increases, we know that the penetration will also increase, and as a result the ultimate tensile strength of the part in the build direction also increases. So this is the typical trend used to be followed when we increase the current in the case of wire arc additive manufacturing. Now let us discuss about the defects we usually face in the wire arc additive manufacturing process. The first major defect is residual stress and also distortion. So residual stress is the remaining stress in the part after removal of all the forces. The residual stress in the part may lead to distortion of the part and hence loss of its geometric accuracy. It is also adversely affect the fatigue life of the part. If the residual stress into the part is more than the UTS, the tensile strength of the part itself, then it will lead to the cracks. And if the residual stress is less than the UTS and more than yield strength of the part, then it will lead into the warping. It will permanently warp the component. It is almost impossible to eliminate the residual stresses from the parts built by wire arc additive manufacturing. However, there are some mitigation methods to minimize the residual stresses while building the part, and also after completing the part, usually a post-processing operation is performed to eliminate this defect. To understand the generation of the residual stresses in the wire arc additive manufacturing, two popular models are used. One is called as the thermal gradient model and another is called as cool down phase model. Let me try to explain to you that how these residual stresses are generated into the part. We know that when the material is deposited at the center of the arc, the region will be in the molten state. So what you are seeing here is the molten pool. And as this region expands due to the thermal expansion, then of course the nearby area in the substrate will be having a compressive load on it, because this expansion of the molten pool will compress the nearby area. As a result, what you are seeing here in this curve, the stresses will be negative in that case in the workpiece. However, after the arc passes away from a particular location, that region start cooling, and due to the cooling it got shrink as well. When it got shrink, the molten pool, it pulls the nearby material towards the center. As a result, the tensile residual stresses getting generated into the workpiece, and they usually follow the curve shown here in the green color. And the final, after completion of the process, usually the tensile residual stresses remain into the part. And please note that the tensile residual stresses are more dangerous as compared to the compressive residual stress. Even the compressive residual stress in the part are favorable for us. For example, if there is any crack or porosity inside the part and there are tensile residual stresses into the part as well, the residual stress, the tensile residual stress will try to open that pore or crack, right? And it will, if there will be sudden load, it will, instead of closing it, will try to open it and may lead to the failure of the part. While if the compressive residual stresses are there in the part, they will try to close all the pores or cracks those are occurring during the process. Another defect in the wire arc additive manufacturing process popularly seen is the porosity. So porosity is the common defect observed in the part produced by WAAM. The porosity in the part will lead to a component with low mechanical and fatigue life. The porosities are classified into two broad categories. One is the raw material induced porosity and another is the process induced porosities. The raw material induced porosities usually come from the contaminations on the raw material or on the substrate, while the process induced porosities usually come because of the poor tool path planning. So as you can see here, what is the meaning of this poor tool path planning is, for example, if you are depositing a bead on the flat surface, right, and it is having a this type of contact angle, that is I am calling as less than 90 degree. Now if I deposit another bead adjacent to it, definitely it will nicely overlap and there will be no unseen region from the top while depositing this particular bead. But if your first bead itself is deposited and having a contact angle greater than 90 degree, in that case if I deposit another bead adjacent to it, for example this one, it will leave some porosities at the region which is not visible from the top, because all the material may not flow due to its finite surface tension into this cavity, and hence it will leave the porosities behind. This is only one reason. There could be few more reasons due to which the porosities can occur, particularly because of the poor tool path planning. The another one was due to the surface contamination. This is the porosity I myself has faced when I was building a part by aluminium. So what I did when I was depositing the material by using the wire arc additive manufacturing, I was machining it as well, and while doing the machining I used the coolant, and that coolant used to have the organic components in it, and when we deposit the next material, those organic components produces some gases, those escape and leaves the porosity behind. That is why whenever we perform any wire arc additive manufacturing operation on any surface or pre-built layer, make sure that it is clean enough and free from any contaminations. So there are the few ways of eliminating or controlling the porosities in WAAM. First is an AC MIG welding process or cold metal transfer, particularly for aluminum, should be used to eliminate the issues related to porosity. High quality shielding gas and use only non-organic piping for feeding the wire through. If the pipings are organic, definitely during the high temperature, these compounds will escape by creating some gas and leave the porosity behind. We should prefer to use a high quality feedstock. We should be very much focused on the bead shape. If the bead shape is having a very high contact angle, in that case we should not choose those process parameters correspondingly. We need to monitor the process closely, as well as we can perform some post and in situ processes to eliminate the porosities. The another defect is the crack and delamination. High temperature and material characteristics are the major reason for crack and delamination in the part produced by WAAM. Following are the two types of crack usually occur. First is called as the solidification crack and another is called as the grain boundary crack. So the solidification crack usually occur due to the obstruction of the solidified grain flow or high strain in the melt pool, while the grain boundary crack occur due to the difference between the boundary morphology and the potential precipitation formation or dissolution. Delamination between the adjacent layer occur because of the delamination between the two layers usually occur because of incomplete melting between the two layers, and this particular defect cannot be repaired after getting it. Therefore, to prevent from this particular defect, we need to make sure that the sufficient melting is happening of the pre-built layer or the substrate before depositing the next layer. Sometimes preheating is preferred before depositing the next layer to eliminate this type of issues. So basically, this particular slide, which is taken from this particular reference, summarize that how these defects are more severe or less severe for a particular material. So color here, the red color is shown here correspondingly for the titanium. This color is for aluminum, this is for steel, this is for nickel, and this is for bintel. So here you can see, let me consider only one example and then you can go through in detail. Let me consider the titanium. It is more severe for the oxidation related defects, because titanium is very reactive material, and immediately when the arc passes away, the hot molten material or the deposited material get exposed to the environment and immediately get oxide. Other than that, the issues such as delamination, the residual stresses, the deformation, the porosities, the surface finish and the crack are not as severe as in the case of oxidation in the case of titanium. However, different material exhibits and shows their different severity corresponding to the different defects, and those can be further studied when you are going to deposit a new material. So now let us see the different variants of the WAAM. The first one is when we use the serial kinematics and no support is used. In that case, a simple 3-axis machine is sufficient enough. Here you can see a 3-axis CNC machine which is retrofitted with a welding gun, and simultaneously on the same machine we can perform the machining operation as well as the deposition process. Also, not only one gun, you can mount multiple guns also on the same machine to deposit two different materials subsequently and appropriately in the desired region. So this is the video for an example of 3-axis CNC based MIG welding WAAM. In this case, you can see the MIG welding gun is mounted on the spindle head of a 3-axis CNC machine, and it is depositing the material on a substrate. At the gun cannot tilt in this case. It can be noticed that there is no possibilities of realizing the overhanging features. Of course, a very small amount of overhang can be obtained because some amount of material can be sustained due to the surface tension of the deposited material. However, the large overhangs, those will require the support mechanism, are not possible to build on the 3-axis CNC machines. As it is a retrofitment on a CNC machine itself, simultaneously machining can also be performed. Such processes are called as hybrid wire arc additive manufacturing processes. So here we first deposit the near net shape on the part and then we finish mill it on the same machine to obtain the final finished object. Now let us discuss about the wire arc additive manufacturing system, those used to have the multi-axis kinematics and capability of building the overhanging features without any support mechanism. So this is the video by Gaffertech, and in this video you can see that the welding gun is mounted on a X, Y and Z axis and the substrate is mounted on A and C turntable. Now I can appropriately tilt the part also in order to obtain the desired overhanging feature. It is again a serial kinematics only, but you can see the appropriate tilt of the part gives us the freedom of depositing the material at a very large overhang. So here you can see the part is tilted in such a way that it captures the droplet vertically under the gravity. The similar phenomena was adopted by us also in IIT Bombay, and you can see that the features are deposited based on the requirement. The center feature right now we are depositing in the 3-axis and there is no overhanging feature in that. After completion of the center portion, then these blades, those are shown here in red color, are going to be deposited and they will be required the higher order kinematics. So now you can see the bottom table is also tilting appropriately. So this higher order kinematics helping us in realizing the overhanging feature without using any support material. So after repeating it, ultimately you will be able to have a near net shape as you are seeing in this diagram. And later on the same can be finish milled to obtain the final object. Also, instead of using the conventional 5-axis CNC machines, one can use the robotic arm as well. So here you can see there is a robotic arm and it is depositing the material on the substrate. The only issue here is if you are using a robotic arm for depositing the material, and if you are going to deposit, for example, this type of feature, your gun has to tilt it, not the substrate. Please remember that. And in that case, it will become like overhead welding or vertical or horizontal welding. So in such cases, the process parameter has to be optimized in such a way that you will be able to perform the overhead welding or horizontal welding or vertical welding appropriately. The parameters which you are using for depositing the material in the conventional manner may not be useful for depositing the material on the overhead welding. While in the previous case what you have seen, the substrate was mounted on the tilt table and we can easily tilt that table and the gun was always vertical itself. Okay, in that case we were not performing any overhead welding, while when you use only robotic arm, this case may occur. And that is why in most of the robotic wire arc additive manufacturing system, a turntable is adjacent to it or coupled with it, so that it can tilt the part and the gun can remain vertical mounted on the robotic arm. So I just want to show you some of the example. This is the largest part built by WAAM in Cranfield University, and you see the size of the part built by this. It is of course a very simple geometry, but it was built by mounted a CMT cold metal transfer gun on a robotic arm. Sometimes to tackle with the material like titanium, we used to purge the organ inside the chamber and you can see that a tent like structure here, and that is purged completely. The whole thing is purged with argon and then depositing the material. You can definitely very closely monitor the process by using the appropriate filter image for monitoring these weldings. So some of the examples are shown here. Now what if I do not use a serial kinematics and instead a parallel kinematics is used in the machine tool side? So this is an example of a delta robot used for depositing the material. So the welding gun is mounted at the tip of this delta robot, and we know that delta robot is a parallel robot and it is depositing now material on the substrate. There could be a hybrid kinematics as well for the wire arc additive manufacturing process, and this is an example of the same. In this case, you can see that the y and z axes are obtained by this parallel kinematic, that is nothing but a scissor lift. As you see closely here, when the gap increases, you will get the z axis, and when the whole thing moves, you will get the y axis. And this is corresponding to the parallel kinematics. Now on top of it, the serial kinematics is further mounted. So it's a combination of parallel and serial kinematics, hence called as hybrid kinematics. So with this, thank you very much.